Today, we're going to tackle one of the most difficult problems in the whole of astronomy and cosmology, the origin of galaxies. What we're going to tell today is a complex detective story, and in the end, we're going to end up with more questions than answers. But what I want to do is to take you today right to the very edge of current knowledge. And when I do that, there are bound to be many uncertainties. But this is one of the most exciting areas of current research in the whole of science, and so I want to take you there to see what is exciting people. Now, the upshot of this lecture is going to be that we cannot understand the origin of galaxies without considering the larger scale structure in the universe as well, the clusters of galaxies and the even larger scale structures which we know exist. And the solution to the problems almost certainly lie in the very earliest stages of the universe. And what we hope is that by understanding these processes, we may eventually understand new bits of physics which will be applicable to the whole of science. Well, let's start with the easy bit, and that is how galaxies evolve if we just leave them to themselves. On this slide here, we have got a galaxy, and we've talked about these many times in the past. What they consist of are of stars and gas, and the system is in gravitational equilibrium. The whole of the system is bound by the gravitational force acting on the stars and the gas. Now, we know in principle how these galaxies evolve. Most of the visible mass is in the form of stars, and they evolve in the following way. Here is a graphic showing the whole of stellar evolution on one slide. It's a time-lapse picture of the evolution of a star in which the shutter is opened once every 3 million years. Now, what we see here, then, are stars forming out of large dust clouds and then very rapidly settling down to a long period where they burn hydrogen to helium in their cores. And this lasts for a very long time until the core of the star collapses and the outer regions expand by enormous factor. The outer layers are blown off, leaving a dead remnant in the center. Our own sun is roughly halfway through this sequence of burning hydrogen to helium in its core. Now, this process occurs in all types of stars. And I've got here models of some of the typical stars that we see in our environment. Locally, we see stars which can be as massive as 60 times the mass of the sun and down to around about only 1/10 of the mass of the sun. But all of them go through this same sequence of birth, life, and death. The most massive stars, about 50 or 60 solar masses, they have lives which are only about 1 million years before they die. Our own sun, which is roughly this size in this scale, it has a lifetime of about 10 billion years, whereas the smallest stars we know of, which have mass only about 1/10 the mass of the sun, they have lifetimes which we believe must be about 1 million years. Now, it's very interesting that this is the range of stars which we can easily observe. We don't see any stars with mass less than about 1/10 of the mass of the sun. And the reason for that is very interesting. It is because the temperature in the cores of these stars is not sufficiently great to initiate the nuclear reactions. So there may well be a whole pile of inert stars with mass less than about 1/10 the mass of the sun. And we're going to come back to these stars later in the lecture. So the way in which galaxies evolve is through this great cosmic cycle of birth, life, and death. The massive stars have got very short lifetimes, and so they're very effective at cooking the elements and then sending them back into the interstellar medium. So we can build models of galaxies in which we suppose that the stars are born at a certain rate with a range of masses, and they will then evolve processing the elements, making new generations of stars. Now, this is a very oversimplified picture of how galaxies evolve, but in principle, we can understand why they have roughly their present appearances in terms of this picture. This is one of the key areas of modern astronomy. Many of us are trying to piece together from studies of this type how it is that the galaxies have evolved from their earliest stages to the systems which we see now. Now, so far we've talked about galaxies as if they were closed boxes, that there's nothing coming in from the outside. But indeed, some things can very significantly perturb a galaxy from the outside. On the next slide, we've got a picture of this type of thing which one sees occasionally occurring in the universe. Here we've got two galaxies which seem to have had a sort of unfortunate accident. They've had a crash. And you'll see faintly coming out of the collision these streamers down to the south and up to the north here. And one wonders, can you ever produce this in the sort of model that I've been describing? Well, the answer is yes, we can. And I'd like to show you now excerpts from a video made by Joshua Barnes and Lars Hernquist, who did these computations using a supercomputer at Princeton University. Now, supercomputers are extraordinarily powerful nowadays, and what we're going to look at are models of galaxies in collision in which each of the galaxies is represented by 40,000 points, both the stars and the gas. And so we can now simulate in a computer how galaxies collide. Here's the starting position. We've got one spiral galaxy here, and when the video runs, you'll start to see it really is rotating, and here's another one here. Now the collision begins. The two galaxies are coming in on very close orbits. So far, there isn't much effect, but they're coming in a very close collision, and suddenly the strong interaction takes place. And look what happens. All that's happening here is that the computer is following the gravitational effect on each star and bit of gas in the system. And you see it produces these enormous antennae-like features entirely due to the collision of the two galaxies. Eventually, we see here the coalescence of the two galaxies into one system in the middle. It is certainly worth a very big clap. That whole process that we saw there took about 600 million years. Now, that may seem a very long time, but it's actually a very short time compared with the age of the universe, which is around about 10 billion years. Now, these are such fantastic simulations. I've got to show you another one. What we're going to do now is to look at another simulation, again by Drs. Barnes and Hernquist, but this time we're going to have a little cluster of galaxies consisting of 6 spiral galaxies. Now, they start being bound in a cluster, so the galaxies themselves are held to each other by the gravitational forces, but of course they're moving in orbits in their mutual gravitational field. Now, here are the 6 galaxies, and we'll just rotate the system so that you can see it in 3 dimensions, first of all, before we set the galaxies off on their collision courses. There we are, 6 spiral galaxies in a rather compact group of galaxies. You'll see these galaxies here coalesce very rapidly into one galaxy. Again, very quickly, another galaxy gets absorbed here to make another galaxy. Now they go off in their orbits for a little while. Remember, they're simply the gravitational interactions between the stars which are doing this. Now one comes in. What's going to happen to it? Has a close encounter, doesn't escape from the gravitational field, and starts now to coalesce into another larger galaxy. And then our friend comes back in its orbit, down towards the 2 galaxies there, and crash. You see the way in which the gravitational forces are flinging off the outer stars from the galaxy, and gradually you see what's happening. Under these tidal effects, the effects of gravity, we are beginning to create one single very large galaxy out of what started being 6 simple spiral galaxies. It's an absolutely magnificent demonstration of the way in which gravity can explain so much. Now, what that tells us is that we can explain a great deal of the remarkable phenomena we see in the universe by stellar evolution plus gravitation. But the big question we want to address today is, how did it all start? Now, it doesn't look as if it's a too ambitious program, because we know that on a large enough scale, gravity will always pull matter together. If there aren't pressure forces inside, then any region of the universe will collapse. And therefore, it looks very promising. We know that stars almost certainly form in this way by having a large static gas cloud, and then the collapse occurs within that cloud. But the problem is, we've got to look at the background against which we're trying to make gravity pull the matter together. Now, this is one of the greatest stories of 20th century science. It was only understood relatively recently that the galaxies are, in fact, very distant systems. This is a picture by Sir William Herschel from 1783. William Herschel worked in England. In fact, he died in Slough in the 19th century. And this was his original picture of what the Milky Way should look like. He represented by a box of stars as if it was a separate island universe. Now, it was only in 1920 that Edwin Hubble, the great American astronomer, demonstrated to everyone's satisfaction that, in fact, the galaxies are very distant systems, not too different from our own system. His second major contribution is one of the greatest contributions there has ever been to cosmology. And that was that he discovered in 1929 that all the galaxies are, in fact, moving away from our own galaxy. And more than that, the further away they are, the faster they're moving. Now, let's just demonstrate how it is that we can measure velocities in astronomy. It is what we call the Doppler effect. And I've got on the bench here a police whistle. Now, I hope not too many of you have seen a police whistle, but we're going to do something special with it. We're going to blow air through it so that we get a constant tone. Right, Bryson, let's get our whistle going. You've heard this tone before. And now I'm going to swirl it about my head. Beware, Bryson. Now, can you hear the tone? Thank you. Now, you all heard the tone there going up and down as the whistle came towards you and went away from you. And you've heard this when police cars go zooming by, you can hear the change of tone. Now, if you notice it very carefully, when the whistle was coming towards you, the tone was higher, and when it was going away from you, the tone was lower. And all that means is that when the whistle was approaching you, then the wavelength was shorter, the frequency was higher, and when it was moving away from you, the wavelength was increased or the frequency was decreased. In fact, from the shift in wavelength, the change in wavelength relative to the wavelength of the tone, we can work out the velocity of the whistle. It's just the ratio of the velocity to the speed of sound. Now, astronomers do exactly the same thing, but they use light. They look for the Doppler shift of the light signals from a distant galaxy, and from the ratio of that increase in wavelength to the rest wavelength of any spectral feature, they can measure very accurately the velocities of galaxies. That is what Hubble did. Now, on this picture here, I show a modern version of what it was that Hubble discovered. We've got lots of yellow points on this diagram here, and these are the galaxies. What we're plotting here is their velocity away from us on this axis, and on this axis, we've got something which is related to distance. And you can see that the points lie beautifully along a straight line which goes right across the center of this diagram. It's showing what is known as Hubble's law, that the more distant a galaxy, then the greater its velocity of recession away from us. I've summarized this on this view here. Here's Hubble's law, and we're showing that the velocity of recession of the galaxy is proportional to its distance away from us. If you like, v is equal to some constant times distant, and this constant here is Hubble's constant, the constant in the velocity-distance relationship, which is one of the most fundamental constants in the whole of cosmology. Now, before we interpret exactly what this means, let's look at another aspect of the universe. And the question I'm wanting to ask is, how uniform is the universe on the very large scale? Now, I've got on this next picture a view of the whole of the northern galactic hemisphere on a very grand scale indeed. This picture is showing where the galaxies are lying on the sky once we take away all the stars from our own galaxy. When we look in the center of the galaxy, of the picture here, you can see that we're looking right vertically out of the plane of our own galaxy. When we're looking around the outside here, we're looking through the plane of the galaxy. And that's why the picture gets somewhat murky towards the edge. There's dust around the edge of the picture, which is associated with dust in the plane of our galaxy. In fact, we only get a clear view in the central region of this diagram. But there you can see that there seem to be holes, filaments, lines of galaxies in that unobscured region. Now, we know what the description of that large-scale structure is like. It's like a sponge. And you may notice that a sponge has quite remarkable properties. All the material of the sponge is held together, and all the holes of the sponge are continuously connected through the body of the sponge. And that is how galaxies are distributed in the universe. You can think of the galaxies as being located where the material of the sponge is, and the holes as representing the holes in the distribution. Now, this picture actually corresponds to the relatively local region of space. We can see that one bit of sponge looks very much like another bit of sponge. But is this still true if we go to very much greater distances in the universe? Well, we can do that by looking at only the most luminous galaxies, the most powerful emitters we know in the universe. And one very simple way of doing that is to look at the radio galaxies and the quasars. Now, we find them very easily simply by making a radio survey of the sky. I've got on the next slide a picture of the whole of the northern sky, but now as observed in a radio survey with a radio telescope. This is from the 4th Cambridge survey. This is the North Pole here, and this is the equator, our celestial equator, round the outside. And I've bent the coordinates so that we've got an equal area projection. In other words, the relative positions of the radio sources are properly represented. Now, I want to do 1 or 2 experiments with this one, and I wonder if someone would like to help me today. Yes, would you like to help me? What's your name?
Gabriel.
Hello, Gabriel. Right. Now, we're going to do some cosmological experiments. Now, if you just come around here, you're going to have to do some work on the computer as well. Are you happy with computers?
Yeah.
Great. Okay. Now, I want you to look at this map and tell me if you see any holes, filaments, or anything on that picture. Can you see anything?
There's one in the middle.
Absolutely right. There's a great big whacking great hole in the middle. Now, I'm sorry about that, but that's just because the Cambridge astronomers didn't look at that bit of sky. So let's forget about that bit of the survey. We've got to put our hand over that. Can you now see any holes in that map?
There's one here.
Yes?
Well, quite a few dotted around.
Yes. That's interesting. That's very good. Now, let's come round here, and I'm now going to, we're going to do a computer experiment. We've done a little computer program to simulate this sky But now what we're going to do, we're going to put down the points entirely at random. So if you just press the return button on the computer, let's see what happens. Here we're populating exactly the same picture, but now completely randomly with points. Now, can you see any holes in this picture? Yes, you see there are holes here, here, here. They're all over the place. That's right. Thank you very much. That's lovely. Now, what Gabriel did there was to demonstrate an extremely important point, and that is that if you put down points on a piece of paper uniformly and randomly, you will automatically get little gaps, little lines, little filaments appearing entirely by chance. It's exactly as if you had a piece of paper and you sprinkle iron filings on it at random. Then you know that you would get some points clustered somewhere, you get other holes. But still, it's all uniformly distributed. And what this picture is telling us then is that on the very large scale, when we look at very distant objects, then on the average, the points are indeed uniformly distributed. In fact, that picture of the radio sources is entirely consistent with the radio sources being distributed entirely randomly and uniformly on the celestial sphere. Now, that looks pretty good, but wait until you see this one. Just last year, the Cosmic Background Explorer was launched to study the microwave background radiation. Here is a sketch of that satellite, and it's been one of the most successful satellites ever flown. Its intention was to study the microwave background radiation being the cool remnants of the very hot early phases of the universe. What I'm going to show you now is a picture of the sky, the whole of the sky taken by the Cosmic Background Explorer, but now measurements at a wavelength of 5.7 millimeters. Now, it may look pretty dull to you, but it's all actually fantastically important. We've got, again, the Milky Way running across the center of the diagram, with looking vertically out of the plane here, vertically down below the plane here. And you can see, we can just vaguely see our own galaxy. If I put my hand over the galaxy, you can see that the distribution looks almost totally uniform. Now, the fantastic thing is that this color scale here, this false color scale, is corresponding to intensity variations which are less than 1/10,000th of the total intensity of the radiation. In other words, these little wrinkles that you see here are absolutely minute perturbations on an otherwise totally uniform sky. It's an absolutely fantastic observation. It tells us that when we look at the microwave background radiation, the sky seems to be totally uniform to better than 1 part in 30,000 over the whole sky. We're going to say a great deal about the microwave background radiation and its importance for cosmology in the 5th and final lecture. Now, you may say, what on earth has that got to do with the formation of galaxies? And the answer is that I must ask you just to wait for a moment, and I will show you how the microwave background radiation, when we take it into the past, is, in fact, very closely associated with the problems of making galaxies. So we believe that we can start off by considering our universe to be the same in all directions, and also we've got Hubble's law. Let's now try to put the two of these together to see what is happening in the universe. Now, we've got here our expanding universe, and this is now an experiment in which everyone has to take part. Because you will notice that we've put some galaxies on this sphere, which we're going to expand. And what you've got to do is to fix your attention upon one of the galaxies, preferably the one which is closest to the center of the sphere for you. Now, I'm going to just mark 1 or 2 galaxies on here so that people can see what they've got to do. Let's just mark this galaxy here. And we'll mark this galaxy here. And I'll come round this side and mark a 3rd galaxy. Let me mark this galaxy here. Now, let's make our universe expand. And what you've got to do is to look at the motion of all the other galaxies relative to the galaxy that you have chosen. Now remember, don't look at anybody else's galaxy. Just look at your own galaxy and look at the motion of all the other galaxies with respect. Thank you very much, Basil. Now, I hope everyone got the correct answer. And that is, you will have noticed that when you fixed your attention upon your favorite galaxy, all the galaxies seemed to be moving away from your favorite galaxy. Is that correct? Yes. And did everyone see it happening? Yes. No matter which galaxy you selected? Yes. Let me show you what's happening on this picture here. I've got a representation of a uniform expansion here, where I've simply got this distribution of galaxies and expanded it up to a larger size. And let's just look at this line of 3 galaxies here. You see, what has happened is that this galaxy here has had to move twice as far as this galaxy here in order for the expansion to remain uniform. You see, here's 1, 2 units here. But this galaxy must move twice the distance of this one in order to preserve a uniform expansion. But it has to do this in the same time interval. And therefore, the further away the galaxy, then the greater it has to be moving in order to preserve the uniform expansion. This is what the expansion of the universe is all about. Hubble's law is telling us that the whole universe is expanding uniformly, and that it doesn't matter which galaxy we choose. Every galaxy in the universe will see the same Hubble's law no matter which galaxy you choose. And so what it means is that everybody thinks they're at the center of the universe, and if you squash the universe backwards, everyone was there in a very compact region at the very beginning. I hope that will save me having to answer a very large number of questions at the end of the lecture. Now, there's one other very intriguing consequence of this expansion of the universe, and that is that whenever we have got any expanding gas, then it cools down. Now, I would like to demonstrate how expanding gases cool down, and I need 3 assistants to do this experiment. Now, who would like to help me with this? Would you like to help me? Right. Yes, would you like to come and help me? And you come too. Now, what are your names? Charlie. James. Timothy. Right. Now, I've got to emphasize the experiment that we've got to do, you must not try for yourselves. We're going to do this experiment under very carefully controlled conditions, and you must not try what I'm doing at school or any place else. Now, perhaps you would like to go to that end of the desk, and you come to this end of the desk, and put on the helmets, and then put on the gloves. Right. Thank you. And now your task is going to be to let off something which looks very like a fire extinguisher at this sheet of felt. Okay? So if you take up this sheet of felt and just hold it up like this, one hand at the top, one hand at the bottom. That's lovely. And now we've got this thing that looks rather like a fire extinguisher. You'd like to hold it. Now perhaps if you hold that nice and tight in the center, you move right close to the center here. And now when I say go, fire it. Go! Good. Thank you, that's fine. Good, well done, thank you. Thank you very much. Thank you. I must emphasize, you must never try that experiment. We've done it here under very carefully controlled conditions with helmets and gloves. It's dangerous because what we've created here is a great deal of solid carbon dioxide. If I put my hand on it, it's very cold. Don't you try this. But what it demonstrates is that the temperature of the compressed gas inside this cylinder was at normal room temperature. When it expanded out through the nozzle, it cooled. And it's demonstrating that when a gas expands, then it cools. Now, the same happens in the universe, because it means that if we take the universe and squash it back in time, then it's going to get much hotter than it is now. And indeed, that is part of our reason for believing that our universe started in a hot Big Bang. In other words, in the beginning, the universe was very hot and cooled down to its present temperature. We're going to need that fact in a little while. Now, how do we make galaxies then? Well, at the first sight, it looks rather simple. We simply take a large bit of gas and allow it to collapse under gravity. But there's a problem, and that is that the galaxy now has to form in an expanding universe. Now, I'm going to use this same large model universe again, but now suppose that this is a little density enhancement in the universe. In other words, there's the rest of the universe round about it, but this sphere here has just very, very slightly greater density than all the surroundings. Now, what we're going to ask then is, what then is the gravitational attraction of this sphere for itself? What is the force which is pulling it together? Well, it looks as if it's satisfactory, but there's a problem in that as the sphere continues to expand with the universe, the force of gravity acting on it is going down, just because the matter is being dispersed, and although it's slightly denser than its surroundings, it is still being dragged apart by the expansion. Now, this has a rather important effect upon the way in which things collapse. We're going to demonstrate this by computer simulation, and again, I need another helper from the audience. Who would like to help me this time? Let me see, who shall we choose? Would you like to come and help me? Are you good at computers? Okay, that's fine. What's your name?
Graham.
Right, Graham. Now, you just come here. Now, we're going to show the difference between an ordinary pole collapsing if we were sitting on Earth, and also what happens to a pole if it so happened that gravity decreases with time. In fact, I'm showing gravity decreasing as the inverse square of time. So all that means is that gravity is getting weaker and weaker as the pole starts to fall, right? So what we're going to do is to put in the initial angle of the pole. Let's put in 0.5 degrees. Good, and if you press enter, right, we'll set up the pole. Now, you can see in both cases, the pole starts off just being at a slight angle to the vertical. And now, let them fall. Just press return again and see what happens. Right? Here they go. Notice that this pole on Earth collapses in the usual way. It is an exponential collapse in which the pole is increasing its angle by the same factor in equal time intervals. But look at this pole. It's really having a hard time. It's not falling exponentially at all. It's falling linearly with time. In other words, it's only increasing its angle linearly with time. And I've just stopped the computation here. You see, it takes a very, very long time indeed to get anywhere. Now, that looks bad enough, but let's do another experiment. Let's press return again, and we'll get ourselves back to the beginning. And now let's put in a tiny, tiny, tiny angle. Let's put 0.0001 in. 1, that's it. That's right, and now press enter and we'll see the poles. We've set the poles up again, but they're now almost vertical. In fact, you couldn't set up a pole this accurately. Now press enter to see what happens. Well, it takes a little while to get going, but remember, exponential growth always wins in the end, and eventually off it goes, crunch, 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 bang. And that's how exponential growth works. It keeps doubling the angle, and it's a very good instability. Whereas this chap here has got a hope. He's starting from a very, very tiny angle, and is simply increasing linearly with time. Thank you very much. That was excellently done. Now, this illustrates exactly the problem with trying to make galaxies in the universe. It's a desperately slow process. Because of the expansion of the universe, the instability doesn't grow exponentially, but only linearly with time. And it means unless we put in a big fluctuation to begin with, we'll never make galaxies by now. Now, that looks bad enough, but there's much worse to come. And that is that we want to look what must have happened to these perturbations in the universe, these little enhancements, when we go back in time. I've got here a picture of showing how the universe changes from the Big Bang here to the present universe here at an age of round about 10 billion years from the beginning. Now, when we go very, very far away in the universe, we look very, very far back in time. And in particular, I want to go back to the time when the universe was only about 100,000 years old. Now, at that time, the universe was much hotter than it is now, and its temperature was about 4,000 degrees Kelvin. When that time happened, then there was sufficient energy in the particles to split up the electrons and protons from hydrogen atoms. In other words, the hydrogen atoms were split up into protons and electrons. It's what we call a plasma. Now, a plasma has a totally different interaction with radiation as compared with ordinary atoms. In fact, the radiation gets very violently scattered, and in fact, it's just like looking at the surface of the sun. The surface of the sun is at a high temperature, around about 6,000 degrees, and you never see inside it because the radiation is continually being scattered. Now, in the same way, in our universe, when we get back to this time, the radiation is then being very strongly scattered by the matter, which has now all been split up into protons and electrons. And it gets hotter and hotter, and the coupling gets closer and closer as we go back towards the Big Bang. In fact, the microwave background that we see, this radiation in the microwave wave band, which was the remnant of the hot Big Bang, is in fact coming directly from this surface when the universe was only about 100,000 years old. Now, the problem comes from the following line of reasoning. You see, the galaxies can only form by growing very, very slowly under gravity. And so we can work out what the size of the perturbations would have to be on this surface here, what we call the last scattering surface before the radiation propagates to us here on Earth. And the answer is that we would expect rather large perturbations, rather fluctuations on the sky, which would be reflected in the microwave background radiation that we see now. Now, many calculations have been done of this effect, and it turns out that the fluctuations should be round about 1 part in 1,000 in size. We should see fluctuations in temperature of about that amplitude on the sky. And that's all wrong. Because you remember, in our picture of the microwave background radiation, it was completely smooth at the level of better than 1 part in 30,000. And this is the big problem about making galaxies, that the microwave background, this remnant of the hot Big Bang, is fantastically smooth. And yet we see a universe now which has got large holes, filaments, clusters of galaxies. And the big problem is how to reconcile these two very key results. Well, how do we do this? Well, we're not certain how we do it, but I will tell you what the current thinking is. Now, I've got a terrible confession to make, and that is that I have not told you the very disturbing fact that astronomers do not know in what form most of the mass of the universe is in. And I do apologize, we've got through to the middle of the 4th lecture, and I haven't told you this appalling fact. Let me show you where the evidence comes from. Here's a picture of a spiral galaxy, a giant spiral galaxy, and we can measure the mass of this galaxy using the same techniques that one uses to measure the mass of the sun. What we've got here is a model of a galaxy, and we're going to set another galaxy in orbit about it. Here is a galaxy. And what we're going to do is to set it in orbit about another galaxy. Now, this might be a galaxy, or it might be simply the outer regions of this galaxy here. But the way that we measure masses in astronomy is simply to allow the outer parts of the galaxy or a satellite galaxy to move around the galaxy. we can measure the velocity of the galaxy by its Doppler shift. And then, just as we can measure the mass of the sun, if we take the velocity of that galaxy and we take the distance it is from the center, we can get an estimate of the total amount of mass within the orbit of the galaxy. Now, the thing which we can do nowadays is to measure the orbit, measure the masses of the galaxies out to very large distances. And indeed, if I simulate this by sending my galaxy, or this bit of interstellar gas, out at a very large radius, you can see that we can now measure the whole of the mass within its orbit, way out beyond the normal optical image of the galaxy. When we do that experiment, we find the remarkable result that there must be about 10 to 20 times the amount of mass that we believe should be there if the matter only consisted of stars. In other words, there must be some invisible matter present in the vicinity of the galaxy that we cannot see. Now, there is the same problem when we look at larger systems like the clusters of galaxies. And we're going to show you how we measure the mass of a cluster of galaxies. Here's an image of a beautiful cluster. There's a large galaxy in the center, but you can see there are galaxies all over this image. And what we have to do, once again, is to measure the velocities of the galaxies within the cluster. Now, however, what we've got to do is to be able to measure the velocities of them throughout this bound system. Now, we're going to do a demonstration here in which I'm going to require two rather tall assistants. Do I have any tall assistants around here? Would you like to come and help me? Would you like to come and help me? What are your names?
Stuart.
Richard.
Stuart and Richard. Thank you, Stuart and Richard. Let's come down here. Now, you just come round in front of me. Here, that's good. Now, what we're going to do is we're going to set galaxies, or rather large ball bearings, in orbit inside this hemispherical ball. Now, I'll give you a big one and a small one each. I'll put mine in, and then if you can put yours in as quickly as you can afterwards, try not to hit them too hard, okay? All right, here goes. Tremendous. What we're simulating here, but very, very much speeded up, is how the galaxies behave in a cluster of galaxies. And in fact, what we did, we've made a frozen frame of the same system. Here are the 5 balls, 1, 2, 3, 4, 5 balls, all rotating in the cluster of galaxies. And of course, this is exactly what we obtain when we take a picture of a cluster of galaxies. We take a freeze frame picture because we cannot see the motions of the galaxies. They are only orbiting in the cluster on a time scale of roughly 1,000 million years. But again, we can use the Doppler shift to measure the velocities of the galaxies. And from the size of the cluster and from their velocities, we get the mass. The problem is, we again find that there must be about 20 times more mass present than we would expect from the light of the stars. And this is what we call the dark matter problem. There is invisible matter in the universe, dark matter, which must be present there, or else these systems wouldn't exist, but we just cannot see it by any means except through its gravitational influence. Now, just to indicate how much dark mass there must be in the universe, I'm representing it by these scales here. Here, I'm putting in the amount of visible mass that there is in the universe. Now, we are certain that there must be at least 10 or 20 times that amount of mass in the form of some form of dark matter. So I'll put that on that side of the scales. When we go to even larger systems in the universe, there may be even more dark matter. And in fact, some cosmologists believe that there has got to be a very great deal, indeed, of dark matter in the universe. And so what it means is that our universe is totally dominated by dark matter rather than by the matter which we can see. In other words, the galaxies are simply the tips of the icebergs, and there must be all this dark matter hidden underneath. Now, there are two problems. First of all, how much is there? And we've already dealt with that question. The second is, what is the nature of that material? Now, I've got some examples of what the dark matter might be here on the bench. Anything that does not have an internal source of energy will be very difficult to detect. You see, we cannot see things in the universe unless it emits light or else it absorbs light. We know stars are there because they shine brightly. We know that there's dust in the universe because it absorbs light. Now, planets are rather dull things. They don't have any internal energy sources. And so one possibility would be that there's a great deal of just simply planet-like material. An alternative, that some of these very, very low-mass stars which cannot burn hydrogen into helium in their cores, there could be a number of these objects around in the universe which would be very difficult to see. These objects are called brown dwarfs. And again, there are great searches for these going on at the moment. Possibly there could be a large number of black holes. Here's a rather large black hole. They're very, very difficult to see unless we feed them one way or another. And again, experiments are being carried out just now to work out whether there is enough matter in the form of dark holes to make up the missing matter. Now, these are what you might call conventional astronomical objects. But what is exciting many scientists is the possibility that the dark matter may be in some form of unknown but remarkably exotic particles. Now, so far, we've been dealing with what we call ordinary particles, things like protons and neutrons, and we're pretty happy with that. But the modern theories of particle physics are now producing a whole slew of very exotic particles indeed. And here they are here. You see, they were all in psychedelic colors. They've got amazing patterns. They've got quite amazing properties. But the only point is that nowadays, particle physicists are predicting in the best theories of elementary particles that there should exist many exotic particles which we cannot measure in the laboratory. And the interesting question is whether the dark matter is in fact composed of these sorts of particles. Now, the one key thing about these particles is that they must interact very weakly with ordinary matter. Now, how is it that these very weakly interacting particles can help get round this problem of the uniformity of the microwave background which we observe on the sky? We have to go back to this very important picture which shows the last scattering surface of the microwave background radiation which we observe now. Now, in the early epochs, before this time, before 100,000 years, the matter and the radiation are very tightly tied together. But the dark matter is not tied to the matter or radiation. And therefore, we can have very smooth matter and radiation here, but we can have fluctuations developing in the dark matter. The dark matter perturbations can develop through these epochs here and into the epochs corresponding to the more recent universe when the matter becomes neutral. So we can preserve the surface which represents the last scattering surface for the matter and radiation remarkably uniform, whilst there are already large and significant perturbations in the dark matter. Now, I'm sorry it's such a horribly complicated picture, but that picture I've described is what people believe is happening in the universe in order to make galaxies. Now, the best way of showing what happens is to show you a simulation made by Edmund Bertschinger and James Gelb, which shows how galaxies may form in one of these dark matter universes. This is, again, a simulation made on a supercomputer, one of the most powerful computers that is available. And in this simulation, they have followed 2 million particles and then followed the way in which these dark matter particles will evolve in the universe. Now, we're going to start off by showing you where the simulation begins. The simulation only begins 120 million years after the beginning. And that is because, you see, we cannot make galaxies without putting in some wrinkled structure to begin with. And we can see here on this picture the large-scale perturbations that are present in the initial phases of this model. Then what they do is to allow the whole structure simply to evolve under gravity right up to the present time. In the simulation, in this bar here, we're going to go from around about 120 million years right up to the present age of the universe, about 10 billion years. Right, let's let the simulation go now. And watch what happens. Now you see the matter is beginning to clump under gravity. You see large holes are being created, filaments of galaxies. And in particular, you can see many of the bits of dark matter are coming together to form large cluster-like structures here down in the bottom corner of the picture. Here, individual galaxies forming. By the end of the simulation, you will see that we've made a large, great cluster down here in the bottom of the simulation. It's a magnificent demonstration of what happens in the expanding universe. So what we've seen on these pictures there is the way in which the dark matter forms these large wells in the universe, and then we assume that the ordinary matter, the protons and the neutrons, will simply fall into these structures and make our own galaxy and other galaxies. Now, does this model work? Well, sort of. What I'm going to show you are some simulations by Carlos Frank from Durham University, which show the types of problems that one tends to find even in the best models. In one version of the theory, this is the predicted distribution of galaxies on the sky. This is where the particles are assumed to be very massive. In this case, we don't quite find enough holes in the distribution. And so we've got to put some extra bits of astrophysics in to create them. Alternatively, we may have very light dark matter particles, and that is shown on the next picture. Here, we are far too successful in making these very stringy structures. In fact, everything seems to be in these strings. So neither of these models seem to be quite right. But you see, I promised I would bring you right to the frontier of knowledge. I didn't promise I would explain everything. The catch here is that we believe that the dark matter is intimately involved in the way in which large-scale structures like clusters and galaxies and the large holes are formed, but we haven't yet been able to find exactly how we get what we observe on the sky. The other beautiful realization is that there may be here a relationship between the large-scale structure of the universe and all of these exotic elementary particles. And in fact, the high-energy particle physicists are trying to take over the whole of the early universe. And the reason is very simple. They cannot get, with terrestrial accelerators, up to high enough energies to test their theories. And so they're using the astronomers' early universe as the only accelerator where the energies are high enough to test their theories. Well, this is wonderful because it's yet another example where astronomical observations may well be the only way we can answer in the near future some of the most fundamental problems about how we can tie together the fundamental forces of physics. And that is a very exciting area of science indeed. Well, I'm sorry, we've done a great deal of very hard work today, many very difficult concepts, but what we really want to do now is simply to observe the universe. What can we do observationally in order to understand more about these problems? Well, I'll give you just one simple example of what we can do. The quasars are among the most distant objects that we can observe in the universe. Here is a very distant quasar. It emitted its radiation when the universe was only about 1/6 of its present age. In other words, we're looking very far back into the universe when we observe this quasar. And what has been found from surveys of these distant quasars is that there seems to be very strong changes in their properties as the universe evolves. On the next slide, we can see a representation of what happens. Here is now, there is the Big Bang. And when the universe was only about 70% of its present age, there seemed to be many more quasars much more quasar activity than there is now. Now, we don't know how that relates to the processes by which galaxies form, but it does mean the universe has changed very dramatically from the time when it was only about, say, 25% of its present age until now. The other things which we can do are to try to find the very distant galaxies themselves. And indeed, I've been working recently on one of the programs which has discovered the most distant galaxies that we know of. We are able to see changes which we hope we will be able to relate to the way in which galaxies form. What we need to do this are very powerful telescopes indeed. Here is an example of the William Herschel telescope in the Canary Islands, which is operated by the UK, by Spain, and by the Netherlands. And this is the most powerful of the 4-meter telescopes there is in the world at the moment. We need extremely powerful telescopes like this to be able to see these distant galaxies. Another way of doing it is to use the Hubble Space Telescope. And in a short time, we expect to be able to see some of the most distant galaxies there are and the large-scale structure of the universe in the distant past with this type of telescope. We have not solved the problem by any means of how galaxies formed. What we've had to do is to put into the beginning of the universe fluctuations out of which the structure will form. This is only one of 3 other major problems which we're going to have to address in the 5th and final lecture. We believe that the solution to all 4 problems lies in the very earliest stages of the universe, and we will tackle that in the next lecture. Thank you very much.
There's a competition associated with this year's Christmas lectures. If you'd like details of it, then please write to the Royal Institution, 21 Albemarle Street, London W1X4BS, marking your envelope competition.